All right, hey guys. So today we're gonna be looking over lesson 2 for the third ACSL competition, and that is data structures. Okay, and so we're gonna be going over 4 basic structures, which are stacks, queues, binary search trees, and priority queues. Right, and so these data structures are just different ways to store information. Okay, and they may seem daunting at first, but once you understand the fundamentals of them, it'll be much easier to understand the more complex aspects of the topics. So diving right into it, we're going to start with stacks and queues, right? And these are just different ways to store data that we want to process later. Okay, so starting off with stacks, right? We have 2 pieces of data right here that are stacked on top of one another. All right, and so the way stacks work is that data is coming in and being stacked on top of it, right? Think of it as like a list or a pile of data. All right, we're bringing data in and we're stacking on top of it to store it. And so now when we want to use this data, process it later, right, we're gonna have to take it out of the stack. So what we're gonna do is we're gonna take the topmost data. So like the way we take out data is from top to bottom, right? So when we're putting data onto it, it's from like bottom to top, right? We're stacking things on top of each other. And then as we want to take them out and process them, to take them out of the stack, we're going to be taking it out from the top, right? Out from the top. And so this sort of order is called let's see if I can manage to. It's called a last in, first out order. Okay, LIFO or LIFO, whatever it is. That's basically what this is, all right? The last pieces of data that come in are the first ones to leave the stack, all right? And then queues are just like stacks. They're like lists or piles of data, but they work the opposite way for the order, okay? So the way queues work is that we'll stack data on top of the pile, right? But then when we want to take data out, the first like the data that was first placed, all right, the data at the very bottom, that's the data that gets taken out first, right? So the rest come down. And we're going to take data again. We're going to take that out. And the rest comes down, right? That's how that works. And so this order works a bit differently. It's called the first in, first out order, right? Because the first pieces of data that are coming into the stack are the first piece of data that are coming out, right? So that's how queues and stacks work. So now they have 2 different operations, both of these, right? They share the same 2 operations, which is pushes and pops. All right, we got pushes and pops. And so it's pretty like intuitive the way that it works. It's just the way they work is that let me use these boxes. Okay, so the way this works is that when we push something, right, when we're pushing a variable or a piece of data, we're pushing it onto the stack, right? That's a push, and that's another push. But now when we pop something, we're just taking out the data. Now, of course, pops differ based on whether this is a stack or a queue, right? So if this is, let's say, a stack, right, let's assume that this is a stack, then the pop, like this command right here, this pop command, would result in this topmost piece of data being taken out, all right? Whereas if this was a queue, then the bottommost piece of data would be taken out, and then the rest would just shift down, right? So the bottommost piece of data is being taken out, all right? Pushes work the same way. They're always going to be placed on top, all right? So looking at this set of commands, right? Let's try working through this. We've got push ACSL, okay? So we're pushing A, then we're going to push on top of that C, then another push S, and then on top of that L. All right? And now what we're doing is, in this syntax, is we're setting these pop commands equal to a variable. So we're taking a pop, and then whatever like value that's being popped is whatever value is being popped is going to be stored into this x variable, right? So that's how that works. So now let's assume the question was, what are the values of x and y, right? If we're trying to figure out their values, first we'd be looking at, like, what's the type of stack we're working with. So first let's assume that, what's the type of data structure we're working with. So let's assume that this is a stack, right? So the way stacks work is we take out the topmost pieces of data. So first we're going to take x, right? So we're pop commands just always refer to whatever the end, I guess they always refer to the end of the data, right? It could be the topmost if it's a stack or the bottommost if it's a cube. All right, but they're always referring to the end. So let's assume this is stack. The first command is x equals pop, the pop function, I guess. So we're going to take away the L because that's the very top and this is a stack. And now x is equal to L. And then we're going to do the same thing. We're going to pop and then set that value equal to y, right? So now y is equal to s. And that would be the answer to our question if this was a stack, right? And we're trying to figure out the variables. Now let's assume this is a queue. The opposite would occur, right? Because in queues, the bottommost values get taken out first. Remember, first in, first out. So now x is going to be equal to a, and y is going to be equal to c, because that's the next bottommost piece of data. All right? So that's stacks and queues, essentially. Which is pretty simple. I doubt you guys will have too much trouble figuring that out. And so I think that's enough for that. So we're already halfway done, technically. So great job so far. Now we're going to be moving on to trees, right? So the way trees work is a bit more complicated, all right? So we already understand the notion of trees. Hopefully most of us do, right? It's a basic graphic organizer that we use all the time. It's like basically a bunch of nodes that have branches into different pieces of data, right? Kind of like that. Maybe we'll add one right there. Oops, one right there. All right, this is the basic structure of a tree, right? But now we're not just working with any sort of trees. We're working with binary search trees, okay? And so what this means is a binary tree just means that every node has no more than two other nodes, okay? So a node cannot have 3 nodes, but of course, it can have either one node or just no nodes connected, right? So that's what a binary tree is, okay? And so this is just, again, another way to organize and almost like sort data, right? This is supposed to make sorting through and searching through information easier. So the way we construct a tree, right? Or actually, let me get some terminology out of the way first. So we have this, that, and that, and that. Okay, so this is an example of a binary search tree, okay? Now, the parent is just, the very top node, there's always going to be one very top node. That's called the root of the tree, all right? That's the root. Okay, let's write it. That's the root of the tree. Actually, you know what? No, it's going to make things confusing. You're just going to have to bear with me. The topmost node is the root of the tree, all right? And now there's also parents. And so parents are just a parent node is the parent node for nodes directly underneath it, right? So let's say this could be the parent node of the nodes directly underneath it. All right, so this is the parent of these two, okay? And then these two are children nodes of this parent node, okay? That's pretty self-explanatory. Sibling nodes are nodes that are equal in level, right? These two are sibling nodes because they have the same depth. Depth is just basically how far from the root a node, is. So these would have a depth of 1, both of these would have 1. The root node always has a depth of 0, and these children nodes would have, these other children nodes would have a depth of 2. And now these 3 nodes at the bottom, nodes without any nodes connected to them, like nodes without any children, are referred to as leaves, okay? They're called leaves. They're the bottommost nodes in every tree. On every branch of the tree, excuse me. Okay, and so now we've got that understood, right? Moving on, okay, yeah. So now looking at the way these nodes are organized. Basically, in binary search trees, there's a certain order in the way we decide on whether this node is going to have a left node or a right node, right? There's like certain rules that we have to follow. Every parent node, okay? Every parent node is always going to be greater than, or it's always going to be greater than or equal to its left child node, or left pointer is another way to do it. Pointer to a left child, right? It's the left child is always, or so the parent is always going to be greater than or equal to than its left child. All right, the key of the parent, one could say. So let's say this is 6. That would be the key. That's like the information it stores. Is always going to be greater than or equal to the child, which means this node is always going to be 6 or less. Okay. And now the parent is always also less than its right node. All right, so this can only be greater than 6. All right, so that's how that works. You're gonna see a lot of like like trees with alphabets, right? And essentially the way that that's organized is just A is going to be considered like the greatest letter, and Z is going to be considered the least letter, all right, in terms of value. Okay, so A is always going to be more than the letters that come after it. So the way that this works now, right? Oh, no. Pardon me. I got that wrong. A is the least letter. Z is the greatest letter. Okay, so imagine the later you go in the alphabet, the larger it grows. The same way numbers work, right? So 0, 1, 2, 3. Then we have A, B, C, D, right? As letters go forward, or more rightward, they grow bigger, okay? In value, greater in magnitude. So let's try constructing a tree, okay? With the word Acsl uses American, okay? Or actually, let's try, we'll stick with American. So the way American works is, right? We're gonna start with the root node, or the first letter, okay? And now we have the next letter. So, okay, let me write this out for American. Okay, there we go, American. And so we start out with, actually, this is going to need a lot more room. All right, there we go. So, American. What we're going to do is we're going to go to the next letter now, right? So we've gotten this A done. Now we're looking at M. Now remember, the parent node is always going to be less than its right node and greater than or equal to its left node. All right, so we have to like take a look at this. M, is this greater than or equal to or less than A? And remember, we know that the later in the alphabet we go, the larger the magnitudes become. So M must be greater than A. All right, so that's how that works. Next, we're going to look at E. All right, so first so now we're at E. We're going to go to A. All right, is E greater than or equal to or less than A? Well, it's greater than, right? So now it's going to A has to be less than its right node. So E is going to go on the right because it's greater than A. Okay, and then we look at M. Is E greater than, less than, or equal to M? E is actually less than M, right? And so it's going to go on to the left. So that way, because M has to be greater than E, right? It is greater than E. So E is going to go on the left. All right, so now that E is done, we're going to go to R. R comes after A, so it's going to go on the right. R comes after M, so it's also going to go on the right. Okay? Then we have I. I comes after A, so it's going to go on the right of A. I comes before M, so it's going to go to the left of M. I comes after E, so it's going to go to the right of E. Next, we're going to have C. C comes after A, it comes before M, and it comes before E, so it's going to go all the way on the left right there. Then we have A again. Now, A is not greater than A, right? It's not less than either, but it is equal to. So A is going to go all the way on the left right here of A, because it's the only letter that's equal to A. All right, and then lastly we have N. So N comes after A, so it's going to go on the right. N comes after M, so it's going to go on the right. But N comes before R, so it's going to go on the left. And that's the word American structured as a binary search tree. Okay? Simple enough. Let's take a look at this, see if there's anything else we want to know. Okay. Okay. So one thing we want to look at, right? Remember, each letter has a depth, right? So the depth for, let's actually just write it down. A is the root, so it's going to have a depth of 0. A and M right here are on the first level, so they have a depth of 1. E and R have a depth of 2. And C, I, and N have a depth of 3 each. Okay? And so what this means is that, let's get rid of that. Okay. There. And let's make that a more clear E3. Okay, so these are the depths of all the letters, right? And so now that means that this tree has an internal path length of 15. All right? Has an internal path length of 15. Because that's the sum of all these depths added up, right? 3, 6, 9, 11, 13, 14, 15. All right? And 0 is just 15 plus 0, so it's 15. So that's the internal path length is 15. Okay? And now this tree also has an external path length. All right? So the way that external path length is that each node, right, has the possibility of having a certain number of nodes, right? So there are these things called external nodes. And external nodes are just all the possible nodes that could be added to the tree, right? So remember, each node can have no more than 2 children nodes. So that means like this R can have one external, actually let me get, all right, whatever. This R has a possibility of one external node. So it actually has one external node, right? Because it could have one more. It has the capacity for one more node to go under it. This N has the possibility for 2. And you can't, by the way, you can't use external nodes on external nodes, right? This is only on existing nodes. This also has 2. This is also 2. And this A is also 2. All right? So we have 1, 2, 3, 4, 5, 6, 7, 8, 9 external nodes. And so now the external path length would be, the external path length is the sum of the depth of all the external nodes. Okay? It's going to be that, and that. All right? All the depth, the sum of the depths of the external nodes is called the external path length, right? Which should be 31. Let's see. 4, 8, 12, 16, 20, 24, 27, 31. Yeah. So this tree has an external path length of 31 because the sum of all the depths of the external nodes adds up to 31. Okay. Let's see what else. Let's erase that. Okay, we don't need that either. So next thing we're gonna look at. Let's see here. Okay. So now there's also different ways to traverse this tree. All right. The different ways, there's 3 different ways. There's in order, pre-order, and post-order. All right, those are the 3 different ways we can write traverse through this tree. All right. So in order, all right, first we're going to look over in order. In order is when we... Actually, let me do this. Maybe that would be easier so I don't have to redo everything each time. There. All right, so I'm going to color code that. And so the color I mark these with is going to represent the order we're using. So the way in order works is that we're going to start at the root. We're going to visit the left child first. Or sorry, we're not going to start at the root. Like we're starting at the top. All right, and then what we do is we're going to visit the left child. All right, the root, and then the right child. Okay? So that's how that works. But now the thing is, okay, so it may get a little confusing, but give me 1 second. Okay. So okay, so the way we would traverse through this tree in order, right? We go left node, then root, then right node. Except this node has children nodes of its own, right? So if we were to traverse through this tree in order, we're going to go left, root, right. We're going to go A, because that's the left, then another A, because that's the root. But now we're not going to go straight to M. We're going to go to the leftmost node, right, which is now C. So the way we would traverse is A, C, right? Then we're going to go to the root, which is E, or not the root, the parent, which is E. So it's left, parent, right. C, parent, E. Then we're going to go to the right, I. And then we're going to go up to the, so now we're going to go back up now to the parent of like this whole relationship, because we've completely finished this like relationship, right? So now we're going to assume that this is sort of like a node of its own, right? So this is kind of the left node we just took care of. Now we're going to move on to the parent, which is M. And then we're going to go to the right, which is, sorry, no, we're not going to go to the right. So now remember, we would go to the right, but we're going left, then parent. So, and this R has a child node of its own. So we're going to go to the left of N. So this is N, and then we're going to finally end on R. All right, so that was a little bit confusing. Let's try going through the whole thing. Remember, left, parent, and then right. So it would be A, C, E, I, M, N, R. Okay? That's in order. Now, there's another order called pre-order, which means pre-order is when we do parent, then left, then right. Okay? And so now the way that this would work is, remember, so let's actually just walk through it. You guys understand. Parent, then, so it would be A, then left, so another A, then right, which would be M. And then we're gonna, okay, I see. So, no, I remember how last time M had child nodes of its own, right? And so we went to C, right? But now, the reason we went to C is because we have to go to the leftmost. C is the leftmost node, okay? Now we're just going straight to M, not because it's the direct, like not because it's the right child of A, but because it's the topmost. Because remember, the first thing, it's parent, left, then right. So we just did parent, left. Now this has roots of its own, but it's the parent. So we're going to be starting at the parent, right? The M is the parent of these nodes. So it's going to be AA, so parent, left, right, M. And M is the parent, so now we're going to go from here to left. So E, E, and then this is also a parent of its own, so then C, and then I. Okay, so parent, left, right, and then we're going to work our way back up. Now that we've done parent and we've done left, we're going to go to the right. So now the right of M is R, that's the parent, and then N is the child node, and then we're done. So the way we would traverse through this one final time is we'd go A, M, E, C, I, R, N. Okay? Finally, now we're gonna go to post order. All right? Now the way post order works is we're gonna do left, right, and then parent. All right, and now you guys basically understand the fundamentals of traversing because of the first two, so I'm just going to kind of speed through this one, all right? So left, right, parent. Yeah. So left, right, parent, we're going to go A, and then we're going to have to go to the left, right, parent. And so now we're going to go to the... So we're starting at A because that's the left of the root. Then we're going to go to the right, but that has children of its own. So we're going to go to the left now to start. So now left, parent. No, sorry. So post order is left, right, parent. So we're going to go left, then to the right, which has children of its own. So we're going to go to the leftmost again. So left then, and then right, parent. And then we're going to come here. This is the parent. So now we need to go to the right. Because it's left, right, then parent. Is how we're looking at it, right? So now we're going to go here. Now we're going to have this little node, which is left, right, then parent. So it's going to be N. There's no right, so we just go to R. And now finally, we've done left and right. So we're going to go to M. And then finally, we've done left and right, so we're going to go to A. All right, so then the final so the traversal of this tree in post order would be left, right, parent, left, parent. Okay? It would be A, C, I, E, N, R, M, A. Okay? So those are the three different orders we can traverse in. That's that. And then there's also okay, so there's insertions, there's deletions, and then there are assertions. Okay, those are the three operations that binary search trees have. All right? So we've kind of already covered how to do an insertion just by constructing this tree. We're just gonna, let's say we have a letter, we'll just call it Z, right? We know that, so we're just gonna start at the top, and we know that the parent has to be less than its right node and greater than or equal to than its left node, all right? So we just compare, and we're just gonna follow the path that it takes us to, all right? So I'll just run through this example and you guys hopefully understand. So we're going to compare Z to A. Z is greater than A. Actually, you know what? Let me not use Z. Let me use something that'll end up in them. Maybe we'll do L. Okay? So we're comparing L. L comes after A, so it's going to move down to the right. L comes before M, so it's going to go right here to the left. L comes after E, so it's going to go to the right. But L comes, H-I-J-K-L. L comes after I, so it's going to be coming to the right. All right? And so that's where L would go. That is an insertion right there. So insertions are always going to be ending up at the very bottommost, right? So now we're going to look at deletion. So now let's say we want to delete a node from here, right? What we're going to do is, we are going to delete E. Let's delete M. So the way that the deletion works is that, let's see. Okay, so the way the deletion works is that if we delete a node, right? Let's say that one. What we do is, okay, let's say we delete this node. The way we like shift the tree to fill it, because we can't just have a gap node, right? It needs to be filled up. So what we do is we're going to take the leftmost node, and when I say leftmost node, I'm talking about as well as the nodes below it, right? So this E is going to be taking the place of the M, right? Because that's the left node of M. And then this right node is just going to become a part of this left node, all right? They're just going to include it. And then we're just going to do that. Oops. That. Okay? That's how that works. Let's look at another example. If we wanted to delete, let's say R. That's not too complicated. We would just replace R with N, right? N would just move up because it's the left node. Let's assume that there was another one called, like, I don't know, E. E, we would just move that there and then have and pop on like that, right? Okay. So that's that. Now, do keep in mind, see, actually this would be incorrect. You need to correct the order. E comes after N, so it would actually come on the left right here. I mean, sorry, E comes before N, so it would actually be on the left right here. That would be the correct tree, I believe. So that's deletion. And then finally, there's search, right? Which is just as easy as insertion. Let's say we're looking for E, right? We're just gonna start at the top and then just make the comparisons we need to find it. So E comes after A, so it would be to the right. E comes before M, so we'll go to the left, and boom, there it is. All right, you're just making comparisons using the whole left has to be, like, the parent has to be greater than or equal to its left child and has to be less than its right child. Just using those properties, you're going to make comparisons to try to find whatever it is you're looking for. And that seems to be trees in its entirety. So we're done with that. Next is priority queues. Now, this is a tad bit more complicated. So the way priority queues work, right? Let's see. So the way it's different from a binary search tree is that it can only delete the smallest item, and it can only retrieve the smallest item. Right? Like the bottommost data, I'm presuming. And the way to implement a priority queue is using something called a heap data structure. All right? And so the way that works, the way that heap structures work, is that every node is going to be less than or equal to both of its children. All right, it's always going to be less than or equal to both of its children. So if this is 6, both of these have to be greater than or equal to 6. Okay, both these children nodes. That's how that works. And once I work through the example, you find out that there's never any holes, right? Just like, you know how in like a, I don't know why I did that. In a regular binary search tree, before we had, or actually let me do American. We had A, M, E, C, I, R, N. You see how there's like a huge just gap right here, right? Missing, like this is a very unbalanced tree. There's another gap right here, right? Actually, I don't know. I don't think that counts. But right here, there's an enormous gap. All right, this tree is very unbalanced. the heap structure avoids that entirely, okay? So basically it's the idea that the parent node is always going to be less than or equal to both of its children individually, right? Like this is always going to be less than or equal to this. This is also going to be less than or equal to this. All right, don't think like the sum of these has to be greater than that. Individually, these always have to be. And that's the relationship between them individually. And then, so the way that we add nodes, I guess you could say, is we're just going from top to bottom, left to right, okay? So like let's say we're just making a heap structure. The way we would work through it is blah, we'd go left to right, then down because it's top to bottom, then left to right, then down, left to right. That was not the prettiest tree, but you see how there are no holes. This whole tree is extremely balanced, right? Actually, it's perfectly balanced. It's symmetrical. And of course you could have like, I guess like a missing like node here or there, but that's only because we haven't added enough data to complete that, right? This isn't really a gap. It's just a possibility for further nodes to go. So that's how we like take care of creating heaps, right? On a fundamental level. Now, remember, there is a rule that the parent node has to be less than or equal to its children. So that slightly complicates things, okay? So we're gonna, let's make a tree right now, or not a tree, let's make a priority queue with the heap structure using the word American, right? Let's see how much it changes. So American, let's just work through it, okay? So we're gonna start out with the first letter, A. Okay, and then remember how we add things? We're just gonna go left to right. So next is M, next is E. Simple enough, like at that point, right? Now things get a little bit complicated. So next we're gonna put R, actually no, they don't, not yet. We're gonna put R here because remember we're just going top to bottom, left to right. So we're gonna start at the left, work to the right. All right, so we're gonna get R. We're gonna add another node, and this node is going to be I. Yeah, I. American. Right. Let me write this out so you guys aren't having to keep track of what letters I've done. So we've done A, we've done M, we've done E, we've done R, we've done I now. Okay? And so when we're let's see if this will actually let me move it. Okay, I guess we're not allowed to move this. Alrighty then. Okay, whatever. So we have these 5 letters, right? But now something changes. Remember, the parent always has to be less than or equal to the node. Well, if you can see right here, so far with these 4, that's been the case. But now when we add this I here, I comes before M. So it can't be the child of M because it's less than M. And so what we do to fix this is we're simply going to change places, right? We're just going to change places up with, okay, change places with M and I. Okay, that's how that works. All right, we're just going to change places. Now, this is the correct structure because, I is less than A, or greater than A, E is greater than A, M and R are both greater than I, so that works. So then we just continue. Next is E. So the next letter is C. And now, whoops, look, C is less than E, so it can't be below E. So we're going to move that. Okay, we're going to move that down and move the C up. So that way, it's fixed. We got the C. Next is A. So we're gonna just, left to right, add the A at the bottom, and look, we're gonna have to make another switch because A is less than C. All right, so that's how that works. And then finally, N is gonna go all the way right here in the left. Which actually doesn't work, again, because N comes before R, meaning it is less than R, meaning we're gonna have to do a little switch right there. There we go. And that's our completed heap structure for the word American. Okay? Seeing it in action, hopefully it's a bit easier to understand. So that's how we're going to create a heap structure. Next is let's see what else. And so keep in mind, with this structure, the root right here at the top, the root is always going to be the smallest value, right? Because A is the smallest letter, it's going to be at the top. Same thing applies for like numbers. The lowest value is always going to be at the top. So next, what we're going to do is I guess that's all. Oh, okay. Well, it looks like that's all we need to look at. I guess we could. Oh, wait. So this whole idea that the smallest value is at the top is called a min heap. And it says a max heap is also possible, but doesn't look like we're going to be looking into that. So this structure right here, this whole heap is called a min heap for minimum heap because the minimum value is at the very top. We could look at insertion. You guys already know. We just add it from left to right. If it's smaller than the parent, we're just going to switch the places, so on and so forth. A deletion would simply, I'm assuming, shift everything down one. So if we deleted, like, say, we deleted this E, then the C would simply move here, and the R would move there. And then, we just replace and shift as we need to. So yeah, that's heaps. Let's work through an example problem. Okay, so we're asked to find these values, right? X, Y, and Z. And this is a stack that we're looking at. Okay, it says in the question. So we're looking at a stack. And so let's just work through it. All right, we're pushing 3, 6, and 8. So we're gonna push 3, 6, 8, and then we're gonna pop Y. So Y is now equal to 8. Then we're gonna pop 6, pop that off the top. Because remember, this is a stack, and so it's gonna be last in, first out. And since 6 and 8 were the last in, we're just taking off from the top. They're gonna be the first out. All right, so now we just have 3, and then we're pushing X minus Y. X minus Y is 2, or no, wait, X minus Y. So 6 minus 8, that's actually -2. And then finally, we're popping that and putting that into Z. So Z is equal to -2. So those are our answers. And that's that. Pretty simple problem. Some more practice that you guys can do on your own is we have to create a minimum heap with the letters programming, and we're gonna have to tell them what letters are in the bottommost row from left to right. Okay, so let's look at programming. Actually, let's do this. Okay. Programming. I'm just gonna cheat a little bit. Instead of rewriting stuff, I'm just gonna drag individual letters. Okay, perfect. So we're gonna start with P at the top, right? Next is R. So we're gonna go from left to right. Okay. Then am I not able to drag stuff when? Okay, doesn't look like I can. Okay, so P, then R, then we're gonna add O, right? Does this work so far? No. So O actually comes before P. So we're gonna have to switch those two letters. P's gonna come down here, O's gonna come up top right there. If I can manage to move it. There we go. Then next we're gonna move on. We're just gonna take this G, put that right here, make a little connection. But wait, G comes before R and O actually. So G comes before R and O, so G is gonna be up here. And these two get switched to the bottom. Excuse me. He's gonna get switched to the bottom. G is gonna be at the top, right? Because G comes before both R and O. All right. Moving on, we're gonna add another R. That works out fine. Now we're gonna add an A right here. We're gonna add an A right here. Except, if we take a look, we know that A comes before P and G as well, so we're just gonna move A to the top. All right, we're gonna move G to the next level and P to the bottom. Okay. Next we have M. I'm gonna move that there. M doesn't come before G, so that works out fine. Next we have another M right here. Now M comes before both M, R, and O, right? So we're gonna need to move M up to this level, then this level, all right? And then R is gonna have to, R is gonna have to come down along with O, okay? And then we're gonna keep M right there. Next, we have I, which is gonna come right here. Except I comes before O, comes before M, but not before A. So it's gonna be right here. So let's move that. Actually, no, we'll move the O first. There we go. We're gonna move the O down. We're gonna move the M down. We're gonna put the I in its rightful place right there. We're gonna next put the N over here. Right, connect it right there. Oh, wait a second. Wow, we actually really running out of space. Let's move this stuff over a bit so we have room. There and there. So we're gonna add N. Except wait, look. N comes before R. So we're gonna have to replace it right and put that right there. Doesn't come before I, so it's gonna be good right here. So let's move this R down there. And it's at the N up here. And then finally we're gonna add a G because we're moving left to right. Right? And then we're gonna move the G here, except G comes before N. So it's gonna go up to this place, and it also comes before I. So we're gonna move it up here. And then we're going to take the I, move it down to where the N is. We're going to take this N and move it down to make room for the I. And so then we can see that the letters at the bottom row are R, O, R, N. Rorn. That's the answer to that question. So I think that's enough practice. There's a couple more problems on the ACSL website if you guys want to do any practice before starting the test. And yeah, best of luck on the test, guys. I hope you all do great.